Okay, so now our next trick is we did one deformation here where we did the twist, obviously. That was a very specific plan where we specifically had an axis that we rotated around gradually as we went up. That's not a very general purpose, of course, deformer. So for the next thing here, I want to say before we even get to the twist, I would like to deform this such that it's narrow at the top and then it kind of curves down into a wider base so that we can kind of make this reverse tornado kind of look. Then we'll twist it after that. So at first things first, we need to do an arbitrary deformation. What I would like to do, and along those lines, is make a deformer similar to the way we deform polygons typically, where if you have like a sphere, so we have a sphere with a bunch of points, and let's say I have a pig head. Where's my pig head at? There we go. So, you might be familiar with a point deform, for example. Point deform is a very general concept where we have the actual mesh we want to deform, so the pig, and we say we take a rest geometry of some kind, something that's close enough, something like that, and then we have some modified version of that. And it's the modified version that is dictating the end result. So here we go. So this point deform is saying based on where the sphere is going, it's doing an okay job of it right now because it's not a very good example. I'm sorry, but get the idea. I'm only moving the sphere. As you can see, I'm just moving the sphere. And it's binding the other geometry to it. Basically just saying the points that are closest to it are the ones that have, influence on it in a sense. So I want to do a similar thing to the volumes. Now, if only we could actually just use the point deform with the volumes, our life would be much easier. Similar to how if only we could use the twist before with our volume, we would have been done there too. As of this recording, there still is no volume deform, probably because it doesn't come up too much, but it definitely comes up with things like this, where we want to make arbitrary, procedural, cool, magic, really sweet volumes. And that's where this lesson comes in. I'm going to show you how to make a pretty good volume deformer. Technically speaking, probably not the best it could possibly be, but a very, very good volume deformer would get into some more advanced topics that are outside the scope of this lesson. What I'm about to show you is quite good and still, dare I say, better than most volume deformers you're going to find on the internet. So let's get to it. I still want to do the similar principle where I'm going to have a piece of geometry that will define the rest, and then we're going to deform that geometry to say this is where you're deforming to. So let's rough this in. So here's a box, 16 by 16 by 16. Let's do the thing where we copy the y size, paste relative here, times 0.5. There it is. Now I can make this taller if we need to. 28 will probably work again as usual. I'm just going to go a little bit higher to 30. And let's also do a polygon mesh. I want to have some extra resolution should I need it. We'll start with 2 for now, a regular box, but we'll increase it later as is needed. So we've got a box. The box is good, but what's even better are tetrahedrons. I want to basically break up whatever my input geometry is here, in our case, this box. I want to break them up into tetrahedrons. Tetrahedrons are 4-sided pyramids where each side is a triangle. If you want to see what that looks like, bring up a platonic solid. The first example of it is a tetrahedron. There's other ones in here. Cube, if you've heard of that. Octahedron. These are all basically Dungeons and Dragon dice. Utah teapot, maybe not so much. Anyway, tetrahedron is a pyramid that looks like this. This is a way to break up volumetric space, meaning just 3D space. Voxels do that, but voxels are cubes. Tetrahedrons actually do it a better way, in a sense, depending on what better means here, and that they only need 4 sides. It's a 4-sided shape to do it, instead of a cube, which is a 6-sided shape. what's the property of tetrahedrons that I'm most interested in is the fact that normally when we talk about points in space, we're talking about points that have an x, y, and z. X-axis, y-axis, z-axis. We can also define a point, though, in terms of where it is inside of a tetrahedron. So imagine if I had a point, I'll just make a sphere here. If I had a point, and maybe I'll make a demo for this. Don't hold me to that. If I have a point here, and it's right in the middle, it's kind of the average of all 4 points of this tetrahedron. If I have this over here, if I'm doing a weighted average of these points, it would be mostly this point of the tetrahedron, and not as much as these two, or these 3 rather. Of course, if I was somewhere like right here along the side, I think you get the idea. It's like kind of medium strength, these 3 points on this side, and not that much of this. But just think of it as a weighted average of the different points in the tetrahedron. It's not 100% what it is, but it is more or less that. And so we can now define a point in space, not in terms of where it is globally in x, y, and z, but in terms of where it is in a tetrahedron. Now, if we have something that's made out of many tetrahedrons, the point would then be defined by which tetrahedron, like tetrahedron number 12, it is in, and then where it is inside of that tetrahedron. So in that way, it's a whole new way to define points.